Hello and a warm welcome back. Today on the kitchen counter and not on the bench is a toroidal transformer with a primary 240 volt primary on so far, and an a screen, don't know why I said electro, with a screen on there, and that's just two layers of copper tape stuck together with a wire on, and obviously they are not touching each other, so it's not a shorted turn. So I've got insulation underneath there, everything's cushy, and this is the start of a new amplifier build. The amplifier is going to be a 20 watt Class AB2 2C34 triode, push-pull triode amplifier. Well, it's push-pull parallel triode sort of thing. As well as this power transformer, I'm going to be having a go at winding the output transformers as well. I'll get into more detail on that, and I will also try and get into more detail about amp design. The cord I'm using is too big really, but it's all I've got, and so with money in mind, economics in mind, I'm trying to use what I have and not spend money on things that I don't have. And so to start off with, I wrote everything down, what we would need. So I'm going to be designing the amplifier myself. I mean, the design is basically done. I know what it is because I've already built a smaller version of this amplifier before. And so to start off with what power supply you need, you have to write everything down, and that means looking at all the data sheets and lifting information off there and working it all out. So for instance, I know I'm going to be using 4 2C34 double triode output valves. Looking at the data sheet, the maximum HT anode voltage, plate voltage, is 300 volts. I'm using 316 here as a figure because some voltage will be dropped across the output transformers and some voltage will be dropped across the choke if I use a choke. I'm not quite sure about that yet. So we also need to know what current HT wise we need. So looking at the quiescent current of 2C34s, that's 30 milliamps per triode, and so we then just multiply it, and so we'll need 120 milliamps because we've got 4 triodes. So you times that by 1.5. I'm using this figure which I've used in the past, and that gives us 180 milliamps. Let's call it 200 milliamps. Because I'm winding the older transformers, I can build them to whatever spec I want within reason. So then we get that 316 volt figure, we divide it by 1.414 and that will give us our peak voltage or AC voltage that we want, the AC winding. And so what I do then, which is a bit generous, I add 10%. So you just get your 223.5, divide it by 100 and you get 2.23. Times that by 10, you get 22.35. Add that to the 200 and we get about 245 volts, 245.85 at 0.2 amps, 45 VA. Write that down. And then I go through for the heaters and all the other valves that I'm going to use, and we come up with a figure in the end of 121.8 VA. So this toroid core that I'm using is way too big, but never mind. And then what I did, I stripped the secondary off the power transformer, off the toroid as it was. It was two big 28 volt windings at about, I don't know, 7 amps. Took those off, wound on 10 turns, measured the voltage, and that gives me a voltage for 10 turns. Remember, that's unloaded, so you always sort of add a bit on just to be on the safe side. Once I have put some windings on there, which I'm going to do in a minute, we will have a better idea of how much voltage per turn we get, or per 10 turns. And so I put the 10 turns on, measured the voltage, that was 4.9, measured the length of those 10 turns, that was 7 foot 4 inches, and you just extrapolate from there. So you know, you've got to find out how many turns, blah blah blah, all the rest of it. It's just basic maths. And then we end up with some lengths of wire that we need and all the rest of it, and it's all pretty simple. So to start with, I'm going to be winding the first heater winding, and that is just 15 foot of this wire. I could use a lot thinner wire. Basically, as you can see, I'm doubling it up. So to try and, instead of using really thick gauge wire, I prefer to use 2 thinner gauge wires in parallel, and they're just connected at one end to a bit of wire. Wind around and round we go, and then we shall measure it at the end and load it at the end. I'm going to load it first with a resistor, and then I shall actually load it with the actual valves to make 100% sure. Here we are sometime later. I've made sure that I've got 242 volts, which is my usual mains voltage ish. I'm just going to knock this one off here. I've got too many turns on, as you'll see. Meter's reading AC. So we've got 8 volts for about 15 turns, so we need to take some off. If I connect a load to that, a 5 ohm load, that drops down, what is that, 35, that drops down 35 milliamps. Right, let me have a think. The problem is though that the actual valves will probably be different to a fixed resistance load. Right, I thought I'd film this. There we go with the valves on. Knocked off 3 turns, 6.35. I'm happy with that. I have noticed that the valves will, the valve heater voltage changes if they're powered up. So I suppose some heat or whatever is taken away or something with them, you know, actually like working as valves. I don't know. So that gives me how many turns we need then for the next one, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 turns, and we're right. So I shall continue on and whack a load more turns on. I've got, no, hold on. How many have I got? 1, 2, 3. I've got 3 heater windings on there, and they're all 6.8 volts unloaded, which is good. The 2 for the 2C34 are actually lower current than the other ones. So what I shall do, if I've got space, I shall just fill this up with heater windings, and then that makes all of that layer the same level then, if you're with me. One practical consequence of using a bobbin like this, is it a bobbin? Yeah, whatever, bit of wood with to wrap the wire around, and when you wind in two sort of turns at a time, you end up with all this sort of nonsense. And so as you go, you have to try to sort of straighten it all out, and I use a sort of glove for this, you know, an old glove, not one for them posh light gloves that you see some mechanics use and all that. Just an old glove will do. That just sort of protects the old fingers, and then just get the kinks out, and then what I do, I just sort of, so I've got like fingers like, you know, 2 fingers like that, and then I'm just sort of pressing it, can you see, like that, and then I'm running that along the wire. A bit hard to show you, sorry. Running that along the wire to straighten the wire out, and that makes it lay down better, because I mean I can never get it as good as a machine, as neat and all that, but what I'm trying to do is get it all to lay flat, all to lay nicely, and to get as many turns in for the space that I've got. And so that's what I end up doing more than anything, is just actually making sure it's all laid nice and as neat as possible. What I'm also checking every so often, well all the time, is making sure that all the turns that are going down here aren't crossed over like that. That's a big no-no in transformer winding. And to do that, which I've mentioned several times in my video, I just knock up these, like, you know, wooden tools, and they're like really good for, you know, manipulating wire. Same as this, I mean it's just a split piece of wood. Saves your fingernails obviously, and you can just use it to place the turns as they go round and round. There we are the next morning. Got all the heater windings on, plus one spare, and I have covered it all in Captain tape. I wasn't going to use this thin stuff because we've got a HT winding going on next, and so I've got to bung all that lot on there. It's quite a lot. It's going to take me a while obviously, and there's going to be more than one layer. There's only one way to do it, and that's to crack on. See you in a bit. Some moments later, as Mark says. That's a good point. I should change my name to Mark. I might have more success with electronics than I am doing at the moment. Anyway, as you can see, I've got one layer of the HT winding on, and I've checked it, and it's about 87 volts, which surprised me, because usually when I've wound these things, after about 1,000 turns you only get about 47 volts, which is disconcerting. So I shall just keep going round and round and round until I've finished all this wire on this bobbin. See you later. Here we are at last, towards the end now. We've got, oh, somebody's been messing with my tripod. What's somebody done here? So we've got, what was that? Few turns left on the bobbin. I thought actually I would have to add some on because I ran out of wire, but if we look on the meter, 10245, we've got 234. Let's whack a load on that. I've got a 1100 ohm resistor on that. Wow, that's fallen to 129. Okie dokie. Right, I think that's a little bit too much there. There we go. I've got 3K9 on there. I'm not quite sure what that equates to. What's that? 217. So still need to whack a load of turns on. I'll do the maths properly in a minute, but it just gives us a rough idea. Right, so keep going and get this finished. Right, ready to start on the last winding, the bias and what do you call it, constant current source supply winding. It'll be at about minus 60, it'll be at 62 volts, but it'll be a negative rail, as it were, as opposed to a positive rail like the HT. Right, I've only got that much to put on. It's about 100 foot. No, it's more than 100 foot. Yeah, no, it's 100 foot. About 100 foot to go on. So maybe about one layer. We'll see. Alright. Well, that didn't take long. It's not the most brilliant of winding. I had to sort of space it out a bit to try and get to the end and everything, but there we go. 70 volts. Don't know what that is loaded. It'll be fine. There's not a lot going on there. About 60 milliamps, maybe 70 milliamps. The wire's plenty thick enough. So with that, I shall bungle this stuff, plastic stuff, back on, and that's it. It's done. And then on with the output transformers, which will be fun because I've never, well, I have wound a few sort of ish, but anyway, we'll get on to that when we get there. Fucking something's eating the bloody shed workshop. Anyway, there's the mains transformer for the new amplifier, all wound with this horrible clear non-sticky whatnot stuff. It's horrible to work with, and yeah, what have you, but there we go. I just reused the stuff that was, you know, that came off the original transformer. That'll be fine. So that's all done. So what have we got? We've got 5 heater windings, a screen somewhere. That's not the screen. That's not the screen. No, that's the screen. So that's the screen. I just mark them with dots. So that one is heater 5, that one is heater 1. So the green ones are the heaters. This one here, the blue one, is the negative bias winding. The red ones, we've got 3 red ones. So we've got, I think it's what, 254 volts AC, something like that. And then what I did to use up all the wire that I had left over, I did another tap, so that's like plus about another 10 volts. And then this orange one, I wound on the rest of the turns, and that's just another sort of winding, as it were. I can either add on, or even if I wanted to, I suppose I could use it as a buck or boost sort of winding. But anyway, and then obviously that's our mains wiring, mains wires to the primary winding. So a mains transformer is pretty simple to do because it only works at one frequency. That's either 50 or 60 hertz depending on where you live. Now then, we've got to get on to winding an output transformer. An output transformer is a totally different fish, in that we want it to be able to run on lots of different frequencies, so anything from sort of 10 hertz up to 30 kilohertz, say. And to design the output transformer isn't easy. Winding it isn't easy either. So let's go into the control room and I'll try and show you how I went about it. I'm not going to be able to give you a step by step, this is what you do to wind a transformer, because this is my first proper one that I'm winding, so I don't want to give you any information that is incorrect, and I'm not experienced enough. But I'll show you how I went about it, and I'll show you what sources I looked at to figure it out. So before we even, these are some of the sources I looked at. We've got Radio Designers, what do you call it, manual by F. Langford Smith. This is the 4th edition. As you can see, it's a massive reference material, book. It's quite hard to read because it's written in the sort of 1950s, 60s, and really, if you'd have done like a degree in maths or electronic engineering, then it will make more sense to you. It also uses inches and all the rest of it, so you obviously have to bear that in mind, because I did all the measurements and calculations in metric. It's easier that way because the laminations are metric. So you've got radio designers. We've got this one. This is a PDF that you can get off online. It's by a guy called Walpert, Designing Audio Transformers. Ian kindly gave me this book. This is Transformers for Tube Amplifiers by Igor S. Popovich. It's a good book. I mean, it does go into a lot of detail, but even though there is sort of a step by step, see here, it's wrong. Some of these formula here on this page are wrong. I know, because I did it, and I've spent literally 6 weeks, not every day, but keep banging away at this. So there's that, and then I'm going to point you at the screen, and this is what I followed in the end. This is Patrick Turner's old website. It's been saved on DIY Audio, and this is what I find the most useful and the most straightforward, but even this isn't straightforward, so it's not an easy proposition. So where do we start first? If I just move all this off here, and I will go to here. Right, this is the data sheet, one data sheet for the 2C34 double triode, which is what I'm going to use. And if you're going to design an amplifier, you first need to know how many watts do you need, how many watts, and what you're going to do it. Are you going to do it in push-pull, class single-ended? If it's your first design, if it's the first time designing a valve or tube amplifier, I would recommend you go for push-pull. It's easier. The power supply is easier. Everything's easier. So you start off with the data sheet, and that gives you some parameters. So like here we've got, this is in class B, you see, but it doesn't give you everything. You have to iterate or like build a prototype. So we've got the HT, our anode or plate voltage. It gives you a grid voltage, it gives you an output. More importantly, it gives you a plate to plate or anode to anode resistance or load, impedance properly. And here it says 10,000, basically 10k for those circumstances there. So first thing you do, get as many data sheets for the valve that you want to use as you can, because most data sheets will give you the same information. Some data sheets will give you more, and I would recommend you choose a valve or tube that is pretty common, like an EL34 6L6. I would recommend you do that because there is a lot more information online and there are a lot more data sheets. For this valve here, this twin triode, this is meant as an RF transmitting valve. So really it isn't particularly suited to audio frequency amplification, but it is. Some RF sort of triodes and pentodes and all the rest of it are easier to use in an audio amplifier than others. Some won't even give you like a sheet like this, which is the most useful. So the basic data sheet that you want to start using is this one, which is DC plate anode volts versus DC anode plate current with the grid lines on here. So in this amplifier I'm going to have to go Class AB2. That means driving the grid into grid current, which is usually a big no-no, and to do that I'm going to use a cathode follower. So that gives you your lines there, and then basically you start off with a load line. As mentioned, if you go to, I would recommend you look at the Valve Wizard's website, which is a primarily a guitar amplifier, Valve guitar amplifier sort of website. But Merlin there, he's basically gives you everything that you need to know, how to draw a load line and all that. I think I did a video on how to draw a load line. So moving on, you draw your load line, or you just take your conditions here, and then that gives you your load. Right, and then you design your, basically you start from your output stage and then work your way sort of that way. Right, next, if we go to Patrick's site, Pat Turner was a self-taught audio amplifier builder, mainly, you know, valves. Really clever bloke, and he basically gives you everything you need to know. So the first thing I think you need to start off with, let me just pause you there, and right, looking down here, so as you can see, look, I've got, I mean, forget that, I've got pages and pages of calculations, doing the same calculations from different sources over and over again. But you basically start on, you decide on your maximum power, your primary impedance, your Z impedance, which is what I was just going about, and then we want to know the lower 3 dB point, or we want to know at what frequency, what is the lowest frequency that we want the output transformer to be able to reproduce without distortion. Having done that, you then calculate the cross-sectional area of the transformer that you need, and he gives you the formula that you need. But basically the cross-sectional area is this here, that's your cross-sectional area, and you need to know that because your lowest frequency of the output transformer that decides how much iron you need. And we need to know the HT, or the rest of it. Right, I came up with something like the cross-sectional area I would need for a 22 amplifier with, I think, a 14 hertz lower frequency, 1407 millimeters squared, for 25 watts, 1500 millimeters squared. Now then, Ian kindly sent me a load of laminations and bobbins some time back, and you need to use the right lamination material, Goss, 3% silicon steel, but you're going to have to look into that yourself. So there's no easy way to do this. You are going to have to get your head around it yourselves. So there's our bobbin, and that gives you pretty much dictates everything from now on in. So after we know that, after we've done that, then we need to work out how many primary turns to put on, and then it's a matter of just keeping going through. So you've got an idea of how many turns to get on, then you've got to calculate, can you get all those primary turns on there if you use such and such a wire gauge, and then you just keep going through it, more calculations, You need to work out as well the primary inductance in Henrys that you need as well. The more turns you put on a output transformer, the more the bigger the inductance. The bigger the inductance, the lower frequency you can reproduce without distortion. And so you basically just keep going through it, working out the turns ratio and all the rest of it, and then it starts to really get complicated because there's basically two areas of output transformer design, and that's a low frequency sort of part of it, and that is determined by how many turns you got on the primary inductance, the how much iron you've got, the core area, that dictates that. And then the higher frequency component, to work that out, I didn't bother with that. Basically I sort of stopped at, once I'd worked out how many primary turns, how many secondary turns and all the rest of it, I stopped there, and I didn't really go into it any deeper than that. And then after that I just worked out, have I got room, this is called your winding window, if I use such and such a gauge wire. And you also have to factor your insulation in there as well. So it's quite a complicated old McGubbins, quite a complicated endeavour. But one thing to try and keep in mind, if you do get downhearted, basically all a transformer is, it's just a load of turns of copper wire round the core. That's it, really. It is pretty simple, but obviously it isn't. There's a hell of a lot more than that, but try and keep that in mind, you know. And so there we go. Where did we go in the end? So we want 2,150 turns on the primary, and then what we do on a output transformer, you layer it, because we want to, you've got a primary winding and a secondary winding, and we want to make sure that the capacitance between each winding is as low as possible, because if the capacitance is too big, that reduces your high frequency response. And so what you usually do, you put a primary, secondary, and all the rest of it. But in my situation, what did we decide to do? I think we decided to go 2 primary, 1 secondary, 4 primary, 1 secondary, 4 primary, 1 secondary, 2 primary. And that's the sort of thing we're going to do. So I've basically got how many turns per layer, etc. And then I've just got to wind it and remember how to then connect it all up. Because having wound a few transformers myself in the past, I know how easy it is to get lost. You end up with a bit of tape on the end of a wire saying it's such and such. That bit of tape falls off, and before you know it, you're in a right mess. So the practical winding of the transformer, which we'll get onto a little bit later, is also an absolute freaking nightmare. So that is just a brief overview of output transformer design. There is also various bits of software that you can use. There's Delatch. He will sell you a software bundle which will design a transformer for you. There's a free one on DIY Audio, which you go and find it yourself. You'll be better off for it if you actually do the work yourself, is what I'm saying. You know, I can't really say this is what you do. But if you look online and did what I did, you can find out all the answers. Pat Turner's website, my hand again. Pat Turner's website is available if you go on DIY Audio and look up Pat Turner, and it's there. It's basically been saved in HTML form, and there we go. Right, with that I'm going to cut it there, I think, because I have a feeling this video is getting on quite long. In the next episode we'll actually deal with the winding of the output transformer, the practical winding of it, that is, and I might probably go into a bit more of the design. Right, thank you all very much for watching. Take care of yourselves. Ta-da for now.